Okay.
All right, so I start YouTube sharing. Is it fine?
Yeah.
Okay, very good. Let's just. All right. So I am very glad to present Baiying Liu and his talk on automorphic descent from GL7 to G2. Please.
Give a talk in this seminar. So this work is joined with Joe Handley at the University of Buffalo. So section 1. So let me start from the long length. Functoriality. So F is a number field, and so A is the range of values. And then so given say G is a connected reductive group, so we have the root datum. So okay, so if we switch the root and co-roots, so this, and we consider the connected complex group. So that's called the Lagrange dual group. That's what we see. Okay, so so GG check. So SO 2n plus 1, say, and the dual group is SP2n. And if we consider SP2n, it will be SO 2n plus 1C. Okay, and so the group we consider is G2 and split G2, then the group is G2C. So of course, you see we have another one, so GLN, then we have the GLNC. Okay, so that's the Lagrange dual group, and then we can from the Lagrange L group. So the LG, that's the dual group. So same derivative with V group. So the group we split in this talk, and so in that case, this will be direct product, and we just maybe just consider dual group is enough. Okay, so we're going to assume G is split in this talk. Okay, so the Lagrange philosophy of functoriality. So you say we have two groups H and G, and so if there is L homomorphism from the Lagrange L group, okay, and so this factors through the V group. So then there exists functorial map from the automorphic representation of H to automorphic representation of G. So this delta, so such that, so I'm already here, so such that there is some function condition. So the partial function, so S pi, say we have a pi here, and we have L pi, L pi, and it's pi. So we for any finite dimensional representation rho of this LG, so this R, this is R. So R compose rho, so equal to the L to pi. I think that's a border. Okay. Of this R. Okay. So for any finite dimensional analytic representation R. So that's the Lamont functoriality. So so this lifting, functorial lifting satisfy this function condition. Okay. So and S is contain almost all finite places. Okay. So the descent, automorphic descent, so is the inverse map of this functorial map. Okay. Okay. All right. So so let's review the some of the results for the functoriality and lifting for classic group, and then we move on to the G2. Okay. So so let's take one example. So SO 2 plus 1. So the dual group is SP2N C. So this is embedded on GL2NC. So one expect that there is a lifting from representation of SO2 plus 1 to GL2N. And so here we're going to use the R is standard representation here. Okay. Okay. So and so for classic group, so if pi is so generic cuspidal, so this is H, this is G. GL2N here. So so for generic cuspidal spectrum, so that's the lifting. So the work of cocktail. So Kim. Pieteski, Shapiro, and Shahidi. Okay, and so that's for the classic group. Okay, and so for the unit group is Kim, Krishnamurti. So for that's UN, and so there is for the GSpin group, Asghari Shahidi. Okay, and so for the descent, for classic group, and so that's Ginsburg Sturdy. Okay, so that and for the that's including classic group and the UN. So that. And for the GSpin descent, that's work of Handali Sayak. Okay, so that's for generic cuspidal. So and if we consider the so discrete spectrum, the work of us classification. So so Arthur, so it's a quite split classical group, and includes also O2 and inner form. So then the work of Mock, so that's unitary quite split. So and then the work of Kalesa, Mingus, Shen and White. So that's the U and inner form. Okay, so recently, so for the cuspidal spectrum, and there's recently the doubling construction. So doubling construction of the work of Tsai, Friedberg, and Ginsburg, and Kaplan. And then the later of Tsai, Friedberg, and Kaplan. So this doubling method, doubling construction, so they give a new lifting for the cuspidal spectrum from cuspidal group to GL, including GSpin. Okay, so and then follow this doubling construction. So recently, I think just posted online, so Ginsburg and Suri. So constructed the inverse, the full inverse, inverse image. Okay, so the so-called double descent. So that gives the tempered aspect, the full image, for inverse image. Okay, so I also want to point out the work of Jiang Zhang, the twisted, using the twisted automatic descent. So that's library for the Hermitian case and construct the tempered out packet. So so their approach is closely related to the global gangrenous process conduct. Okay, so working with Jiang Zhang, so we are working for the skew Hermitian case. Okay, so general question would be so how to construct each other packet explicitly. I think that's a general question. So all right, so introduce so this descent method using for coefficient attached to newpont orbits. So let me briefly recall that. So we're going to follow the setup of Gomez, Gravich, Sahi. Okay, so so let's take as G is like connected reductive group. Okay, so this G lead algebra, we consider new cone here, and so under the joint action, this new cone is a union of orbits, we call newpont orbits, and so say we take a newpont orbit, we take a representative here. So S is a semi-simple element in the Lie algebra. So this Sx on the Lie algebra is a direct sum of eigenspaces. Okay, so then this pair Su is called the Whittaker pair. So if its U is inside the -2 eigenspace, and so Su is called a neutral pair. So if there exists V such that this VSU is SL2 triple. Okay, so U say it's a Whittaker pair. Then we can form a group. So N SU So that's like exponential of this subalgebra. Okay, so and then so another group, so US, and that is okay. So and then we can define the character on this psi U. So and here, okay, so that the character, the killing form U log n. Okay, so this will be a character of this NSU, and if we take the kernel of that, so we know that the US over this kernel on this, the kernel of this group, a kernel of this map in this group. So that will be a Heisenberg group. So let's denote this one by H. Okay, this will be a Heisenberg group. Okay, so then given given the pi with the automorphic representation of GA, and so we take a form here, so the Fourier coefficient attached to this Whittaker pair would be so integrate this n as U and G. Okay, so that's the with the Fourier coefficient attached to a Whittaker pair. And the nomination is independent of choice of the representative U. Okay, so and so if you let the form run, so this will form an automorphic representation of the group. So stabilizer. So L. So L is the levy. Okay, so the stabilizer of this character inside the levy times H. This will be an automorphic representation here. Okay, so let's see some example. So we're going to use this example later. So say SO4N. Okay, so in this case, for classic group, the newphenomenon parameterized by so partition and quadrat forms. Okay, so say I mean for this one, so 2n minus 1, 1 2n plus 1 this partition. Okay, so for this partition, I mean just the one newpont orbit corresponding, not one, just so there's some choice of a newpont element. So let's say like this. Okay, block here. Okay, so 0 here, 0. Say we see this is a size 2n plus 2, and here so 0 is 0 and okay. Sorry, something wrong. Okay, 1 second. I need to, sorry, the sharing was off. Let me do it again. Okay, so so SO4 and say 2n minus 1 1 plus 1, and so you take this Okay, 1, 1 here. So in the middle. Okay, so as 0 is 2 plus 2, and 0, 0, 1, 1, 1 here. Okay, so I mean we take the and the neutral semi-simple element corresponding to U, and in that case, that's the stabilizer. Okay, the stabilizer of this beside U in the middle there is ISO 2n plus 2 would be the ISO 2n plus 1. Okay, that's one example. And so another one, so is if we consider 4n plus 2, and then the orbit is 2n plus 2, 1, 2n. And so if we take U argumentative like this, sorry, I missed 2 characters here, so something here. Yeah, next one, that's, yeah. Okay, so here, if we take similarly, and in the middle is like is size 0, size 2n, corresponding here. Okay, so and we take the corresponding neutral semi-simple element to U, and in that case, the stabilizer so in the middle there is a SP2n plus. Yeah, so there will be the levy of 0 eigenspace for is 2n plus 2 SP2n. The character here is SP2n semi-direct product with the Hesburgh group. Okay, so that's 2 examples, and okay, so the descent corresponding to 2 examples. Okay, so the first one, so if so is SO 2n plus 1 to GL 2n. Okay, so in that case, say we start from a pi here, and we know that so if pi comes from SO 2n plus 1, so the condition here is the partial function h square has a pole, namely symplectic type. Okay, so in that case, we put GL2n inside the SO4n, and we put it in the levy. Okay, so pi. Okay, like this. So and so this function condition so tell us that the Ascending series has a pole, and we can get the residual representation on this SO4n, and so using the Fourier coefficient corresponding to the example I just gave, so one would get a representation on SO2 plus 1, so that's get sigma. Okay, then that's the descent here. Okay, and so another example is if we consider so SP2n, and then the dual group embedded to GL2 plus 1, and if we start pi here, and we know that types, so namely this symmetrical function as a pole, and we consider the big group 4 plus 2 double cover, and still using the Ziegel parabolic, and so and we know there is a residual representation, a function give you the pole. So and using the Fourier coefficient in the second example I just gave, so when we get a representation of SP2n, so double cover semi-direct with H, and then you integrate with the theta, so you get SP2n. Okay, that's the sigma here. In this case, the descent. Okay. All right. So so now I want to move on to the case I want to consider that's the G2. So for the G2, so the dual group is so G2C. Okay, so embedded into GL7C. Okay, so so one would expect that there is a lifting from G2 representation to GL7 representation, and so actually, so this this embedding so factors through SO7C. Okay, so for the lifting actually, so so G2 there is a theta correspondence between this and SP6 or PGSP6. So and then using a lifting from SP6 to GL7. Okay, so this is theta lifting. So the lifting is for at least for the generic cuspidal representation of G2. So one can do it this way. So is off again. Sorry, I've did it again. Somehow this iPad connecting. So all right. So okay, let's do it again. So G. So okay, so G2, so the G2C, so you embedded the GL7C, and so factors through SO7C. Okay, so for the lifting, so one can, at least for generic cuspidal representation of G2, one can so do this way, so theta to SP6, then using the lifting of Kim, a cocktail Kim, Piazza Shapiro Shahidi, so lifting GL7, or using the work of Arthur or etc. So, but for the descent, so one may ask, can we just go back? Like you see, we have this descent, right? So we just saw this descent, and then apply theta. Can we get something here? Okay. So then the problem is we don't know the non-vanishing is for this here. If we compose, so so the problem here is the non-vanishing. If we use this way, okay. So the approach, so we're working with Joe Handley. So we're thinking, so just go, we don't pass through SP6, just go directly from G7 to G2. Okay, so that's okay. So so we need to just like the previous two examples for Cauchy group, we need to group to them bigger group to construct them as interiors, radial representation, etc. So and we also need to figure out so what kind of representation we need to start with on GL7. Okay, so so there's a lemma. So if so this is G2, GL7. So if this pi comes from G2, namely, so it's like this kind of lifting. So and let's assume it's cuspidal here. Okay, then the condition on pi is, so pi is self-dual, and the wedge cube and function has a pole. Okay, so actually in this case, so this wedge cube function actually has a decomposition here. So so symmetric square and also the standard function. Okay, so that's the condition for pi. Okay, so we're gonna start from this kind of pi. So so if pi satisfies this pole is s equal to 1. So if pi satisfies this condition, so we're gonna so call pi is like G2 type. Okay, so okay, so such pi of G2 type. Okay, and so we're going to start from such pi. Okay, this is analog of so that in the first example, you see we have the big group SO4n and SP 4n plus 2 double cover. So analog of that, so we're going to take the GE7, so which is the levy of E8. Okay, so you see, okay, so that's E8, and we take this levy. Yeah, that's give you, so that's we can, this is definition of G7. So we're going to use this one, this group. So this analog with the big group in the first two examples, okay? And so on this, for the residual conditions, how to, so you see we have this, then now it's G7 now. So we take this levy, and this turns out, so this levy is isomorphic to GL7 times GL1, okay? And we're gonna put the pi of G2 type, okay? And so, and GL1 here with the trivial condition. And here, so we put the second fundamental condition of E8 here, so like omega 2 S, okay? So pi is the G2 type, and the I function can appear in the constant term. So the I function, so in the constant term of this will give you the S series on G7. As in the series on G7, okay? So the I function appear in the constant term. Is so in this case is the wedge cube, and yeah, so plus here, okay? So here just let me just finish. Okay, so and because we assume pi is of G2 type, so this wedge cube have a pole and pi is of 2. Okay, so and this give us, so this as in series has a pole at s equal to 1, and this give us lead us to define the residual condition of E pi. Okay, and this E pi is on G7. Okay, this will be the kernel representation. We're going to do the descent. Okay, so all right, and then you see, remember for the first two examples, you see we have SO. So the big group is SO4 and SP 4 plus 2 tilde. So we need to take some newpont orbits, and here we need to take some newpont orbits on G7. Okay, so the first, so in this case, there are two newpont orbits. Turns out, so two newpont orbits we can use. Okay, so let's see the first one. So the A2 plus 3A1. So this is under the Balakata classification of newpont orbits. Balakata label. Okay. All right, so that's the easy the minimal Levy subalgebra such that it contains a representative newpont orbits. Okay, that's okay. And the weighted Dynkin diagram for this orbits is this one. So all right, so it's so 0, 0, and here is 2. Okay, that's the weighted Dynkin diagram. Okay, so corresponding to this, so this gives us the actually a weight for each root subspace, and And if you take U, so they give us some simple element. So you take some U in general position in the selected 2. Okay, eigenspace. So this one is actually so if you consider so this levy and the opposite. So new radical is actually so wedge cube. So some independent space and some plus because it's 2-step. Okay, and this G negative 2 is actually here. Okay, so it takes some vector here. Okay, and the stabilizer will give you G2. Okay, so this will be a vector here. So in general position. Okay, and then the stabilizer. Inside, you see that we have the levy, the GL7 times GL1, right? So of this psi U is G2. Okay, and so you see this is a Whittaker pair, and they take the Fourier coefficient of the residual representation we just constructed, and this we denoted by d pi. That's the descent, and it's on automorphic representation on G2. Okay, so that's the descent in this case. So and of course you see as you have to show it's non-vanishing and whether it's generic, whether it's cuspidal, etc. So and it turns out in this case, so this is 0. So this d pi is generic. Okay, but it's not cuspidal. Okay, so it supports all the degenerate Whittaker Fourier coefficient on G2. So in particular, it supports the constant term along Borel subgroup, and also the constant term of both maximal parabolic G2. If you take the constant term, you get generic representations. Okay, so this descent is pretty mysterious. So yeah, so and we also consider the local unramified descent, so which is highly reducible. Okay, so it's not clear. So what's this in this representation in this case? Okay, so
but
so this is not a cuspidal actually. So so as far as I don't know, there are some other similar descent. So one of them is the in the work of Ginsburg, so from descent from F4 to G2. In that case, is also not cuspidal, and also so Ginsburg and Handley is also working on from descent from G6 to F4. So they also expect to get non-cuspidal descent. Okay, so unfortunately, we have another newphenomenon. So another one is A5 double prime. And for this newphenomenon, the weighted diagram is here, this one. So 2, 0, 0, 0, 0, 2, 2. Okay. So you see here's a levy, D4. Okay, and again, so some simple element here, you wait, and you take some vector in the negative 2 space, in general position. And the stabilizer of this inside this levy is still G2. Is still G2, yeah. Okay, so and in this case, still you can get the descent by d pi on G2. Okay, so in this case, fortunately, we can okay, so first is generic, hence non-vanishing, and if you assume there exists one place, one finite place, so such that so locally pi v is of G2 type, namely, I mean, is so this subjective parameter is in G2 embedding in the image of embedding G2 to GL7. Okay, is of G2 type. That just use the same notation. Okay, so then this descent is cuspidal. Okay, so for the cuspidality, we need this condition, at least one finite place. Okay, so pi v is of G2 type. So so if we assume if almost all v finite place, so pi v of G2 type. Okay, then we can show that so d pi is so lift to pi. I mean, you reduce summand of d pi. Okay, so lift to pi. Okay, so in other words, so each so if you take a reduced summand of d pi and so it's shared unramified, almost every place unramified select parameter with pi v. Okay, so this theorem tells us that so in order to do the testing that we need, so this theorem tells us that we need pi is like so wedge pole, and so for almost vol v, so pi v of G2 type. Okay, so then so you can construct a sigma such that lift back to pi. Okay, so that's so here I want to make some remark. So you see we have this condition, right? So a remark is so there's some conjecture saying that so we expect so if you start from pi, which is just so wedge cube has a pole, and pi is f2. So then this unramified condition will be satisfied. Okay, so then almost all v finite pi v of G2 type. Okay, so in other words, for this for this functoriality for the descent, so I mean we expect if we just this a function condition plus self-do. Okay, but somehow we cannot show this, so we add this condition that so you see for almost all places is of G2 type. Okay, yeah. Okay, another remark is so we also expect so this conjecture actually equivalent to the following conjecture. So pi is so wedge cube has a pole, and so pi is self-dual, and then so then the condition of Ginsburg and Jiang, so Ginsburg will be satisfied. So Ginsburg and Jiang's condition will be satisfied. Let me explain that in a minute. Okay, we'll hold. Okay, so namely, so let me start. Let's see. So you see, consider so there's a theta corresponding to SP6 and G2. Okay, so and so this representation pi come from G2. Let me use sigma here. Come from G2. There are some equivalent conditions. So the first one is spin 7. Spin 7 a function has a pole, or some period non-zero. Okay, so we expect if so this wedge cube have a pole and self-dual, then one of these equivalent condition will hold. Okay, so actually, so these two conjecture are equivalent to each other. Okay, as suggested by Michael Harris. So so actually these two conjectures are equivalent. Okay, so yeah, another remark is the theorem has been used to this application. Although you see we have more conditions like wedge, Q, or pole, and almost all places of G2 type, but this theorem is already enough to used by Harris, Kaya, so on, to show the surjectivity of the local analytic correspondence. For generic supercuspidal of G2. Okay, so somehow we apply the theorem. I mean, so both the wedge, cube, pole, and almost all places of G2 type, they can both conditions can be satisfied. So they comply the theorem to construct descent, hence to show the surjectivity here. Okay, all right. Yeah, and another remark is so remember that on GE7, so we construct the residual representation E pi. So so there is the version we from set, namely the maximal newpont orbit, such that so this residual representation has a non-zero coefficient. So let's use introduction. So maximal newpont orbits so support this representation. So we expect that this one is the newpont orbit A6. Okay, so we were able to show that so A6 support. I mean, give a non-vanishing non-zero coefficient for this residual representation, but for the yeah, in order to show this is maximal, you have to show the vanishing of big orbits. So for that one, we need like at least. So let me write it down. So this is true. So if there exists a place, a finite place such that pi v of G2 type. Okay. So we also need this condition. In order to show this is maximal, yeah, we need this G2 type condition locally, at least one place. Okay. So okay, I think yeah. So that's the descent from cuspidal representation of GL7. So currently we're working on like for non-cuspidal like Algebraic sum, etc. So descent to G2. Still work on it. Okay, I think that's all. That's all. Thank you.
Questions, please.
Yes, I have a question.
Yeah.
Is you were computing these stabilizers that would turn out to be equal to G2. Are they only these two orbits, or there are other unipotent orbits you can get something like that?
So for G2, there's only two newpont orbits.
Okay. All right.
Further questions?
Can you say anything more about the first unipotent orbit?
Yeah. So first newpont orbit is A6. So we can show that the non-vanishing, but so in order to show that so the big orbit are vanishing, we need one place that pi v is of G2 type, because usually to show the vanishing of some global result, so one go to local. So we need this local thing. Yeah. But we expect that the top is A6.
Okay, but I mean you have two neopotent orbit descent go to G2, right? The first
Yes.
one, and the second one you succeed to get a cusp form.
Yes.
But first one, it seems you get a very big representation. Yeah?
Yes.
Do you know anything more? I think that orbit I tried with Ginsburg a long time ago, but it was not.
Yeah, so it's generic and non-cuspidal and local descent. That means highly reducible. So it's quite local descent. If we just consider local unramified descent, I mean there are many pieces. There are many infinite many admissible double coset. So I mean we didn't investigate further than that. Yeah, and we don't know it's L2, so we don't know which spectrum it is.
Oh, you don't know it's L2.
We don't know. Yeah, we didn't try to. Yeah.
But you know it's generic. We don't have.
We know generic because that's a way to show non-vanishing. Yeah.
Okay.
Yes.
But we know there's like a trivial representation is there too.
Okay. Then. Yeah, that's the
Okay, very good. Good job.
Okay, thank you.
So, more questions, please. Okay, so I have several questions.
Okay.
First, if I understand correctly, there is one fine point in this descent. It is not a priori clear that it gives a z-eigen representation.
Say it again, sorry.
Yeah, may not be
not always the center of the universe developing algebra.
Not always finite, yes.
So you don't require this.
No, because no, we don't. Yeah, it may not be automorphic form. Yeah, right.
I see. Second, could you please repeat what does it mean to be of G2 type?
Yeah, so G2 type. So the wedge cube have a pole and also self-do.
And also self-do. I see.
This is a global condition. But you said there's the local component to G2 type. What do you mean?
Oh, that just means that the local unramified the selected parameter. So lies in the image of G2 embedded G7. Yeah.
Okay.
Yeah.
But your descent is irreducible?
No, we cannot show that. It just irreducible usually is very hard to show. Yeah.
Okay.
Yeah.
You don't expect it?
No feeling. Don't know. Yeah. Yeah.
Another knee-jerk reaction, is there some period condition for this exterior cube having a pole?
We're trying something on this that we haven't got. Yeah.
We don't have integral errors, as we don't have integral for this guy.
Yeah, we are computing something with Joe Handley. So yeah.
Didn't Ginsburg get something for wedge cube? Doesn't he have
Wedge
something?
cube, we only have a GL6 wedge cube. We have period.
Yeah.
Oh, it's for GL7. Yeah.
Like Archimedes said, find me the group and I'll find you the integral.
Right. Kobe.
Is there some general conjecture of what does Langland's functoriality do to wavefront set?
Could you repeat your question, Dima?
Yes. Is there some general conjecture of what does Langland's functoriality do to wavefront sets of representations?
I don't know general conjecture.
I have a very rough conjecture about this, about the upper bound.
Sorry.
Yeah, it's conjecture.
The upper bound, but the precise things it's hard to tell, because if you have generic packet and then there is many non-generic guys there, these guys will share different wavefront set.
And what is the upper bound?
I tried with Baiying to see what's the lowest bound. Originally, if you look at general, like all cusp forms, which may be non-Ramanujan, and then James Lee has a lower bound, which like a common lower bound, so-called non-singular cusp form, right? But if give you particular packet, and then you try to find a lower bound, this is a very difficult question. I think my paper with Baiying in Simon Symposia addressed this question and give some examples there. Right, if you're interested, you can look at that.
Yeah, I know this paper for cuspidal representations, right?
Yeah.
All right. Any further questions or remarks, anyone?
What about GSpin?
What's that? Say it again.
What about
GSpin.
the good GSpin?
What about GSpin? You mean descent?
Yeah.
Descent is, I mean, so how do they say it?
Local work.
Say it again.
The local GSpin.
The local GSpin. You mean our work? Yeah, I'm still reading it. Yeah.
Okay.
All right. Thank you again.
Okay. Thank you.
Good job.
Thank you.
Great job.
Thank you, Dima.
Thank you. So next week we have another summer recess, and in 2 weeks we will have a lecture by Bernard Kreutz
Okay, good.
on
Okay.
Archimedean representations.
Okay, good.
Yeah, we got the announcement this morning.
Yeah. All right. So see you in 2 weeks.
Thank you.
See you.
Yeah, bye-bye.
Bye.
Thank you all for coming.
Thank you.